put some words to that. What is the complication being addressed at the bottom? Those bottom two reactions. To do all of these kind of aldol type reactions, or in this case Claisen, what's our big complication with our Claisen reaction? Our base can act as both a nucleophile, it could also act as a base. Okay? Couldn't it have done that with the aldols? So if I had drawn an aldehyde, couldn't that base have just as easily acted as a nucleophile there? It's a good review of our last chapter.
The nucleophile would act as a good leading group, and it would kick it back out.
So we could form our tetrahedral intermediate. We'd have our O, using ET here. If we have the opportunity to make the carbonyl, to go to an sp2 carbon, we should. So that would reform because we have a leaving group, that leaving group being our OET. Do we have any other leaving group? No. No. So what ends up happening? We get primarily the reverse reaction. What functional group do we make in purple? That's halfway to becoming an acetal. The hemiacetals. And what did we know about our hemiacetals? They were unstable and very quickly revert back to the carbonyl. So again, if we have the opportunity to form a carbonyl, we'd better keep a carbonyl. Okay? That's what we get out of our acetal chapter. The only time we can form an acetal when we form a cyclic acetal, because that forces it to be somewhat stable and allows it to stick around for a significant amount of time. And no other circumstances that really work out for us. So while under the aldol conditions, our nucleophile could act as a nucleophile, it forms an unstable intermediate that very quickly reverts right back to starting material. Okay? So while that was a possibility, nothing really comes of it. Why are we looking at it now in the case of the Claisen? What happens if it acts as a nucleophile? We have a choice of leaving groups. We have the species that attacked, okay, in which case we go right back to where we started, and for that matter, who cares, right, because it's right back where we started. Or, based on the structure I've got drawn here, we had a different leaving group, which means our structure changes. So instead of starting with one starting material, I'm now starting with the potential for 3 or 4 different electrophiles. Is that a good thing? No. Okay. So how can we mitigate this issue so I don't have to worry about it attacking as a nucleophile? Okay. We could try and level up and switch to a different type of base. Okay. We could use a bulky base. We could use an irreversible base. Fun thing about irreversible bases, they tend to melt your face. General safety concern. We want to avoid that if we can. Can we avoid that? Do we have to use an irreversible base? Okay, well, if I'm asking that, quite probably, no, we don't have to use an irreversible base. Right? So now the question becomes why? What base could I use where I do not have to worry about this nucleophilic attack? And where the only result I get is which reaction? The acid-base attack. Why do we do the acid-base attack? So I heard a couple questions along these lines. Okay. Hearing people referencing the double bond. It's a bit of a dicey statement to make. Okay, we don't really want to reference that as a double bond because really what that is in resonance with what species? Describe this one for me. Okay, Okay, you took too long, I'll give you the easy answer. It's negative. It's a nucleophile. What could that nucleophile potentially do? It could attack an electrophile. Are there electrophiles in that environment?
Yes.
Yeah, there's still more carbonyls. Theoretically, those carbonyls could be attacked. Okay? So why am I concerned or looking at this species but not the first one I drew? The one in red is the reactive one. The one in purple is our more stable resonance structure. Okay? So we're looking at our first worst resonance structure to predict something about the reactivity. Okay? Notice from either structure, I can still get that carbon to be a nucleophile. Okay, the one in red, how do I know the carbon's a nucleophile? Well, it's negatively charged. Okay, well, that might have been an easy one. Okay? How can I get the purple one to have that same carbon be active as a nucleophile? Well, to be a nucleophile, what has to happen? It needs electrons. Where does it have to get those electrons from? From the pi bond. But if it picks up those electrons, what would happen to now our blue carbon? It would be positively charged. Well, that's not a good thing. How do we stabilize that? The electrons from our negative oxygen can come down, form the pi bond between our carbon and our oxygen, and we'd have our nucleophile. Okay. We can do any reaction from any resonance structure. It just may involve more curved arrows. Okay. You need to be able to move from either one of those structures out to them reacting with something else. Okay? So, back to the question that I had initially asked, the nucleophilic attack. How do I prevent the nucleophilic attack from coming in there and messing with everything, because this then generates different nucleophiles, and for that matter, electrophiles. Okay. I need something to prevent the nucleophilic attack from generating problems. Can I prevent the nucleophilic attack altogether? Here are suggestions for the bulky base. Okay. The bulky base could potentially help us out, okay, because that'll minimize what? Minimizes the nucleophilic attack. Okay. Well, if it can't nucleophilic that one, they can't do the top one. Cool. Okay, that's a possibility. What else could we do? We tried talking about an irreversible base. That brings in a safety concern that we really shouldn't have to be looking at. If we take that a step further, what is special about the diester and that hydrogen? It is very acidic. If it's very acidic, should I be using a stupidly strong base? No, the issue with using a stupidly strong base when I have a weak acid, I'm upping the level of reactivity well beyond what I need to. I increase the likelihood for other things happening, and I don't want those other things to happen. Okay, we want the bare minimum to get the reaction to occur.
So what she's suggesting is that we can use a weak base that is less likely to act as a nucleophile?
Partially correct. I am suggesting you can use a weak base.
The weak bases don't make good nucleophiles.
The bases that we're going to end up having to use for this will end up acting as nucleophiles. Okay. We have a couple of problems here, and we have addressed the big one in the room, the nucleophilic attack. That is a major issue. Okay. What if I can't mitigate the nucleophilic attack? What if I can't prevent the nucleophilic attack? What do I then need to prevent? What is the issue with the nucleophilic attack? It generates different nucleophiles and electrophiles. The different is the next part of this. We said we can't get rid of the nucleophilic attack. Then what we have to fix is the different. If the nucleophile attacks, it cannot generate a new nucleophile. What base can I use? If the nucleophile attacks, who cares? What does it kick out? It kicks out the exact same thing that was already there. So when you look at your Claisen reactions, you will notice that the ester piece, that OR group, is always the same thing as the base. Always. Why? Because of this massive complication. Okay? We can't prevent the nucleophilic attack. It will always happen. So what we do is we use a nucleophile that won't generate different things. Simplifies things so that now the only route that we really care about is the one where it's acting as an acid and a base. Sets everything up, I can get my nucleophile, everything's cool. Fine and dandy. Okay. Neat little consideration to consider when you're, if you want to consider considerations. Yeah, thank you, Dan, for catching that before I called it out. In our Claisen reactions. So now the next part. The top one. So we had challenges across the room. We had one group saying that we went all the way through to a product, and that product ended up being, forgive me, it's going to look a little bit ugly. I'm going to do it this way. D. Okay. And everybody see that? Agree with it? Okay. So we end up generating, because we have an alpha hydrogen, we have our nucleophile. That nucleophile, just like in our Claisen reaction or our aldol reactions, can come in, attack, form the tetrahedral intermediate, form our tetrahedral intermediate, reform the carbonyl, kick out the leaving group, and we would end up with the product shown. Right? Does everybody see and follow that? Okay. So my left side of the classroom said that this should happen. Right? Okay, do you see anything wrong with it? You guys did it, so theoretically. No, you say no. Pretty quickly. Okay. We do have another alpha hydrogen. So, and Tyler was asking about this, we do have the potential for this reacting a second time, okay, and continuing. That's usually a bit messy and also usually beyond the scope of the question being asked. Okay, so don't stress on those. Those become a little bit more relevant for the aldols and much less relevant for the Claisens. Okay. You start to build so much bulk that it becomes very difficult to do it multiple times. Yes, it can happen, but it's difficult. Okay. My right side of the classroom, you said no, can't do that. Why?
Troy said that you need two alpha hydrogens, but one of the things I'm seeing too is that OH group can squelch that negative carbon. You see the hydrogens, because the negative oxygen is more stable than the negative carbon.
You're saying this?
Yeah.
That's there as a solvent. You're right. It will quench some of it, but then we'll have equally active base to go through and remove the hydrogen again. Okay. So yeah, that acid-base step we do have in a huge equilibrium. It'll take a little bit to actually get it to propagate. It'll still act as a nucleophile eventually. It'll still react with the second equivalent. Okay. So that's not going to kill it. Okay. What Troy was saying, was it Troy that said it?
No, the textbook said it.
Textbook said it. Okay, fair enough. The textbook said that when we run these reactions, we have to have 2 alpha hydrogens. That is a requirement for our Claisen. Well, if the textbook said it, must be true. Okay, it is. But then the fun question becomes, why? Okay. Why is the reaction shown not very likely to occur? Intermediate, which I don't want to draw.
Less of a favor intermediate.
No, same deal as the aldol, the intermediate equivalent energy.
It's not the reactants are more.
Why?
Without having the second proton.
Remember, this is an equilibrium reaction beginning to end. For equilibrium reactions to do anything useful on producing products, what must be true? The products must be lower in energy. Did I make my carbonyl compound lower in energy? No, if anything, it's increased because I have more pi bonds. Okay. Well, what about the leaving group? I have a negative oxygen. Well, oxygen can stabilize a negative charge. What's wrong with that? What did I start with? A negative oxygen. Is there a difference in stability there? No. So the leaving group doesn't help. Our product is higher in energy. Everything about this screams, not going to happen. The equilibrium prevents it from occurring. Okay, well, so why does it need 2 alpha hydrogens? So let's tweak the structure, and let's make one of those methyl groups a hydrogen. So I'll go through and color it in red, which then means I have to color everything else. Okay, which would then mean we have that, right? So that would be the product of our reaction. And somehow or another, the textbook is now saying, well, this is a valid product. Why? What does that hydrogen do? We still have negative oxygen as a leaving group. Still a negative oxygen in our starting material. So no stability in that piece. If we look at our product to our reactant, product is still higher in energy than our reactant because we have 2 carbonyls. What are you suggesting there, Corey? You want to say that again?
Resonance.
What do you mean resonance? I don't see any resonance in that structure that's any different than where we started.
Intermediate is less stable because
If the intermediate is less stable, that's higher in energy, it still says this doesn't happen.
hydrogen is more stable because there's a negative.
Say that again, Tyler.
The hydrogen is still acidic.
This reaction up to this point is still not favored. No product. But what happens if we have that second hydrogen? It is still acidic, which means in the presence of a good strong base, what happens? We would form, God, I should have picked a prettier structure. This thing is freaking ugly. Yeah, and the problem is I've already run out of room because to be able to draw it reasonably, I can't look at it.
You just draw it as the anhydride.
Does everybody see that? What is special about that structure? Now you can jump in, Corey. It has resonance. Said another way, we have conjugation of the pi bonds. Okay, and again, I can't see what I'm drawing. And those electrons could also go this direction. So we have lots of resonance on this structure. What is special about resonance? It becomes more stable. And the product we've formed now can form. Now we have a stable product. That step of the reaction is
Lower in energy.
irreversible because it is significantly lower in energy. But if we go back and look at the answer for this, okay, so is everybody good with what's written up there? Any questions about it? Okay, because what I'm about to do is erase a bunch of stuff, so if you ask questions, I'm mildly irritated. If we look at what the answer is for this question, the answer ends up being that. What we drew and said could not form. Why?
Because it forms, but you get very little of it.
Nope. When we run the Claisen reactions, it is step 1 followed by step 2. And step 2 is H3O+, which will protonate that negatively charged, highly resonant, stabilized intermediate and take us right back to where we started. Okay? The reaction drives forward because of secondary chemistry. Okay? So it's frustrating for students because you look at it and say, well, but here's the product, and you're not telling me I'm not allowed to form this as the product? Why do I have to go and do this other step? We have to go and do that other step because that product, in comparison to our starting material, does not exist. The only way we get that product is through that secondary chemistry where we do the acid-base reaction to form an incredibly resonant stabilized intermediate. We can then add acid to reprotonate back into this stage. That's how the Claisen works. This is why when we run the Claisen reaction, we need 2 equivalents of hydrogen. Why did we not need 2 equivalents of hydrogen for the aldol? Well, we didn't really increase the energy. Okay, in the aldol, we start with 2 pi bonds, and if we just do the aldol, we end with 1 pi bond. We ended up not going all the way to keeping 2 pi bonds. So we do drop in energy with the aldol. What typically happened with the aldol when we added a second equivalent of hydrogen? It very quickly did the condensation reaction. Why? Because the hydrogen is still acidic. If we make the double bond, we have conjugation in it. Everything's great, fantastic, everything's happy. So it's effectively the same chemistry, but we have some kind of limitations or complications within it that we have to watch out for. So when running the the Claisen reactions, okay, so the aldol with esters, you need 2 equivalents of hydrogen for that reagent to work, okay, for that reaction to occur. Questions about that? Okay. There was our acid base generating the new structures. So if we looked at the crossed aldols, what was the result of that reaction? Oops. Probably shouldn't have done that. Sorry, my screen's really dirty. What was the result?
Go to the alpha hydrogen.
Pull the alpha hydrogen. Which alpha hydrogen? Rhymes with a neither. Oh, I can actually accept all of them. Yes, all of them, or either of our alpha hydrogens. We could pull off hydrogens here or here, which means we had 2 nucleophiles. Once we generate the nucleophile, then what do we have to have? An electrophile. Where do we have an electrophile? Here and here. So I have 2 electrophiles, which means I ended up with 4 possible products. And it was a mess. How did we fix that? What was our solution to that?
Make the base the same as what?
The base the same as our leaving group. What's our leaving group? When were we talking about leaving groups? With the Claisen reaction. We're not looking at a Claisen here. This is an aldol. There is no leaving group. One of our starting materials needs to have no alpha hydrogen. If there's no alpha hydrogen, say we go through and add CH3s here. Okay. Now what happens, I only have 1 alpha hydrogen, I only have 1 nucleophile. That can help mitigate it. But then what's the other issue? I still have 2 electrophiles. Why? As a hint, Nope. If it acts as a nucleophile, we end up forming the hemiacetal, which is unstable. We go back to the carbonyl. You want a different hint? What if it was NaH? If we switch that to NaH, we would get one nucleophile again and one electrophile. Ooh. Why did NaH all of a sudden eliminate one of my electrophiles?
Yeah, sure. Because you can remove the hydrogen. It's irreversible is what it is. And so the irreversibility removes the one on the right to react as an electrophile.
Sodium hydride is an irreversible base, which then means it will remove the hydrogen. Okay, and we would have our nucleophile. Okay, don't I still have an electrophilic carbonyl though? Why not?
Because of
Resonance
resonance.
stabilizes that electrophilic position, meaning I do not have an electrophile in that species. I only have a nucleophile. I think I drew it on the wrong side, but whatever. Oh, no, I didn't. Okay, we only have the nucleophile, one electrophile. That was our fix. We adjust the base we used. We adjust which structure has alpha hydrogens. Okay, that's how we fixed that problem. Okay. If we use that irreversible base, we make one nucleophile. We can then react that with one electrophile, and that simplifies our situation drastically. So what happens if we move to the crossed Claisen? Okay, if we had crossed aldols, of course we can do crossed Claisens. So what's going to happen now? Would we expect the same kind of thing?
If your base replicates your leaving group, you get no matter what, you get the same.
Okay, so notice that the base used was O-methyl, and in both our esters we have O-methyl. So we still have the nucleophilic capability of our base, okay, but it doesn't have an effect on our overall reaction because it regenerates the ester. Okay, so this is what we talked about on that last slide. We're making sure that we don't have that as an issue. Okay. So if we aren't concerned about the nucleophilic attack, then what can the base do? Where's the acidic hydrogen? Both structures have acidic hydrogens, which means two nucleophiles. Both structures have the potential for unreacted carbonyl, which means two electrophiles. So the exact same issue that plagued the aldol reactions plagues the Claisen reactions. We have to be very careful to pick esters that either have acidic alpha hydrogens or don't. Okay? We also want to be very careful in our choice of base. We do have one kind of issue with our base choice, though. Can I switch to a stronger base? If I switch to a stronger base, that has the potential for changing out the nucleophile or changing out my leaving group. So if I switch to a stronger base, what has to be a characteristic of that strong base? It can't be a good nucleophile. Okay, like sodium hydride, the base we just looked at. Okay. So, get rid of the alpha hydrogens. We've got a bunch of different structures up there that are great for no alpha hydrogens. Two of which should look incredibly familiar to you guys. And by you guys, I mean just the people in lab. I'll accept the diethyl oxalate, though not officially familiar to you in lab. It's kind of familiar to you, Corey, because you were just working with something similar to that. If we made those CLs, you're right. Okay. And that works very similarly as far as its chemistry. In fact, this is more reactive than the ester. Why is this one more reactive than the ester?
Better leaving group.
We can't say better leaving group because the leaving group doesn't leave in the first step.
I know why, I don't know how to say it though.
Why is our red side more reactive than our purple side? So the leaving group is kind of the example that the textbook went through, but we went through a big activity. Why is the red one less stable? What did you suggest, Sean?
The electrons are being pulled away by the line
Why?
because it's more electronegative.
Chlorine's more electronegative than oxygen?
It's because isn't the resonance?
But if we look at the reactivity to the other side, the oxygen is more electronegative than chlorine. Yes, it's more electronegative than carbon, so chlorine will pull electrons from our red carbonyl. But the oxygen, if we're using electronegativity, will pull just as hard, if not harder, away from the purple carbonyl. Chlorine is so much larger that it has no resonance, which is why we can then look at electronegativity. Okay? The oxygen, being small enough, does have resonance. There's a resonance stabilization of the purple one. There's no resonance stabilization of the red one, which is why the red one's more active. Okay? And yes, that is a challenging one to pick up. So we saw that. We saw that in which lab?
That was what we just talked about was the chemiluminescence one.
Our and I'm just going to leave it there. Luminescence one. Still two more that you need to know. Come on, lab people, help us out. Ethyl benzoate we use somewhere. Where do we use that? That was in making the, I'm going to guess, I'm not positive on this one, but I'll give you a hint. See if that helps.
Malachite green.
There we go. I think that was for our malachite green. Okay, well, just so that you suggested that, the other one that you should have recognized would have been the diethyl carbonate because that was our crystal violet. Right? So there's a reason we use these reagents in lab. It's because they tie into the lecture. Okay? So if we go through and look, those don't have alpha hydrogens, which means I don't have to stress when I mix in the base because the base can't remove an alpha hydrogen. Okay? So I can mix those all together and I really only have one product. Notice the yield is still pretty low. Why would the yield be low if I only have one nucleophile? We could look at it as an equilibrium effect, but we still have two alpha hydrogens, so that should have mitigated the equilibrium effect. So I have the potential for making only one nucleophile. What does that nucleophile react with? Where's the electrophile? The carbonyl compounds. How many carbonyl compounds are there? There's actually two. Our starting material, the one with the alpha hydrogens, has a carbonyl compound. That could explain some of the low yield because while it may be active as a nucleophile, it could likely interact with the same type of molecule doing a self-Claisen as opposed to the crossed Claisen. That's going to drop some of the yield. Okay. We can encounter equilibrium effects slowing the reaction down. Okay. We can see all sorts of other side effects going through that. Okay. Kind of makes sense? Okay. Could we bring in a ketone or an aldehyde?
Sure.
So could we do a cross-aldolazine? Because we're doing an aldol with our ketone or an aldehyde, but we're doing a Claisen with our ester. Is that fair game? Yeah, why not? Brings in a carbonyl, So it brings in the potential for an electrophile. What else does our ketone or aldehyde potentially bring in? A nucleophile with our alpha hydrogens that could react with the base. So it's absolutely fair game to go through and react. Okay? So now the question is, which part reacts? What does our base react with? I'll accept a couple different answers here, specific and non-specific. Okay, so you took too long. Here's your non-specific one. The base will react with hydrogen. So now you got to get more specific than that. Which hydrogen? Well, where is their hydrogen? Alpha hydrogens. Okay, so let's label some alpha. Yankees. We've got some alpha hydrogens. We have more alpha hydrogens? Yep. We also have alpha hydrogens here. Okay, so cool. We went from hydrogen to alpha hydrogen to now what do we need to identify?
Which alpha hydrogen?
Which alpha hydrogen? Where could we get a hint about which alpha hydrogen it's reacting with? Let's look at the product. Let's try and identify the pieces in our product. Maybe whoever built this slide actually had some color coding built into this that might help us out with that.
We don't know colors.
I didn't actually color code it. It's from your textbook.
Well, you don't like it anyway.
Did anybody see any color coding there?
Blue.
Did you really just... You said you can't see red?
I'm sure you were.
Okay, how about this? We'll fix the lack of red. My old advisor was red colorblind. He always carried around a green laser pointer to lectures because it always irritated him when people would come to present and then present using a red laser pointer. So he'd come in with a green one and hand it to him and say, "This is what you're using for your presentation today." So now it's blue color coded and red color coded. If you cross your eyes, it's actually 3D. Okay, what does that do to help us? Where's our nucleophile? Where's our alpha hydrogen that's acidic? It's coming from the ketone. If it came from the ester, what would we expect to see happen? Whoa. We would expect this to be our nucleophile, in which case would we ever see the kick out of a leaving group? Nope. Okay. The leaving group leaves from the attacked or the attackee position. Okay. So we're pulling it from our ketone. Which position are we pulling it from? There's two hydrogens there. So we'll call it hydrogen A and hydrogen B. Which hydrogen are we removing? A. How do you know you're removing hydrogen A?
Because of what? It's connected.
Because we can try and identify how our structure was put together at the end. Okay, so we can cheat and use our product. What if we weren't given our product? What would we be looking for to help us decide? Stability?
Of the, like which alpha hydrogen is most reactive.
If we look at stability, whoops. So that's A. What if we'd removed B? Which one's more stable, A or B?
Negative was more stable on less.
A or B? Which is more stable? Why is B more stable?
More substituted double bond.
The more substituted double bond. Okay, so shoot. We said A was the one that was acidic, and that was the one generating our nucleophile. Why is A doing that? Why are we getting A as our intermediate, not B? And stability doesn't work for us now. No. not quite. You want a hint? My hints have been really good so far today, so that might be why you guys are saying no. Here's your hint.
It attacks the reversible.
It's what?
It's reversible.
If it's reversible, which product do we make?
Thermodynamic.
The thermodynamic. Which of our two, A or B, is thermodynamic? B. So is it reversible? No, it's an irreversible base. You're at least getting at the idea. You just have to refine it. Okay? So it is fine to take a swing and a guess, but then you have to refine and say, what does that mean? If it is a reversible base, we form which product? The thermodynamic product. Reversible base, thermodynamic product. So we would look at our A, B, our enolates. Which of those is our thermodynamic enolate? B. So when you think back to, oh God, I hope I don't ever have to remember that kinetic and thermodynamic stuff. Okay. You either learned it the first time, or you spend the rest of the semester trying to re-memorize it. Okay. Just the way it works. The sodium amide is an irreversible base because we form, or number one, we have a negative nitrogen in comparison to a negative oxygen, which is more stable. The negative oxygen, that says our enolate is very low in energy. That's non-reversible. Non-reversible. I don't know why I picked that word, but irreversible. Okay. What else drives this? When it removes the hydrogen, what do we form? NH3, which would be the conjugate acid of sodium amide. What is the phase on ammonia? It is a gas, unless you're at very cold temperatures, okay, which we probably would be here. Okay. But in the gas phase, that's going to bubble out of solution, preventing the reverse reaction. Okay? So being aware of our energy diagrams, where those things balance out, our kinetics and thermodynamics are all very, very important. They continue to thread through this semester. Okay. If you think back to the Gen Chem sequence, Gen Chem 1, we looked at all sorts of random junk. Gen Chem 2, we looked at kinetics and thermodynamics. You might say, well, that's not all we looked at. Yeah, it is. All you did in 152 was kinetics and thermodynamics. Guess what you're doing in second semester OChem? Kinetics and thermodynamics. Okay. Again and again and again. Exciting stuff. Okay. That should look like a familiar reaction there on the left. What kind of reaction do we have there? We have an intramolecular Claisen reaction. Or that's not Claisen, intramolecular aldol reaction. Okay. Which we just left as an intramolecular aldol. But now what happens? What happens if instead of those being ketones, I all of a sudden change them now to becoming esters? Well, does that really change much of the chemistry?
Seems like it.
Okay, and we'll have to actually make it a little bit longer.
Yes, it does.
We'd have a nucleophilic position which could go wrap around and attack. Okay, which would then kick out a leaving group. And actually, let's see. Yeah, that'll work. Okay, so if we actually move it to being an ester, we have to extend our carbon chain a little bit. Why do we have to extend the carbon chain? If I just made those esters, why would that top reaction not work very well?
You make a four-member ring.
We're looking at that carbon linking up here. 1, 2, 3, 4. Four-membered ring, not particularly stable. So we have to increase our chain length when we move to the Dieckmann condensation, which I would love to pronounce other ways. And if we go through and look at the reactivity, we still have alpha hydrogens. Once I remove that alpha hydrogen, what do I have in that position? If I remove an alpha hydrogen, the alpha hydrogen comes off as H plus, which then means the carbon is Negative, which means I have a, what do I need to do when I find a nucleophile? Find a carbonyl. Getting a lot of people showing me this. Yes, there's a carbonyl right there. That's phenomenal. What did you just show? Resonance. You showed why the hydrogen was removed. That's good. I don't know, everybody's laughing like, oh my God, that's so dumb. That's not dumb. That's perfectly valid. Okay? But all you're showing is resonance.
I was
Okay?
trying to think of what a one-membered ring would look like. That's what I was laughing.
Well, really, it would be a two-membered ring. And we know what a two-membered ring looks like. It looks like a double bond, right? An alkene, that's a two-membered ring.
When I just wrote in my pocket.
We can look for another electrophile, and it could be a second equivalent of this molecule, right? In which case we get a really, really long carbon chain. Or it could be the other electrophile in the structure, and it can loop back on itself, and we would end up forming a 1, 2, 3, 4, 5, 6-membered ring. When that attack occurs, we form our tetrahedral intermediate. So if we drew that out, okay, how I would draw it is I got 6 structured, or 6 carbons there. I want to go back and label things. 6, carbon 6. I like to put nice and vertical here, so I'm going to do 6. Make sure I count through. 5, 4, 3, 2, 1. At position 1, what do I have? I have an ester coming off of it. At position 6, what do I have? I do not have a carbonyl anymore.
Yes.
I have an O minus and an OET. Okay. Do I have the opportunity to reform the pi bond? Is there a leaving group? Yep. I can now kick out the leaving group. I will have reformed the pi bond, and what I should end up with would be that structure. Going through and labeling those carbons, labeling those pieces is very, very helpful. If you skip that step, you're trying to do it in your head, and quite frankly, you're not going to do it right. Okay? So write it out, number those positions so you know how to find it. Notice that we're getting a 63% yield. It's still not super high. Why might it be only 63% and not closer to 100? It could interact with a second molecule. If it does a second molecule, that starts to remove some of the reagent and prevents it from continuing to react. Okay, so what we're hoping for is to get that cyclization. How could we help kind of increase just the cyclization versus the polymerization and continuing to grow? It's an interesting question. For it to react with a second molecule, what has to happen?
Close proximity to just another one of itself.
It has to be close to a second molecule. How do we prevent it from getting close to a second molecule? Dilute it. Add in tons of solvent. If there's now lots of solvent, what's the likelihood that a second molecule is going to be able to interact? Less likely. We should be able to up the yield. Okay. We still have some side effect things going on, but we should be able to increase our yield by adjusting concentration. Okay. So if we think back to another reaction where concentration was a problem. Everybody's favorite reaction. What's another reaction where we have to worry about concentration?
First one we did.
It's not the first one we did, and not the WMK. This is actually, everybody should know this from lecture. Officially from first semester, because we haven't talked about it a lot this semester. What's that? No. All of our radical reactions. Nearly every radical reaction is concentration based. If you adjust the concentration one way or another, you can change the products that you get out of it. Okay? For instance, if we started with if I add in tons of bromine, what do I get as a product? even if there's a presence of light, believe it or not. What do I get? Lots and lots and lots of bromine. What's the product? You had to use that fancy word, didn't you? Is it actually the geminal? Either way, you get that. You get that product, which might be the geminal.
No.
Oh yeah, you sure? Okay, I'll trust you. What if we had only a small amount of Br2? It is not the same thing. Small amount of Br2, we do not get the addition reaction. We get the substitution. We get the radical substitution. You vary the concentration, you can change the conditions or change the result that you get out of it. Okay? So concentration is something that is important. We need to be concerned about and thinking about when we go through and run these reactions. Okay? So now in the next part, we get in a couple named reactions. We get something known as the malonic ester and the acetoacetic ester synthesis. Okay? The acetoacetic ester, why do you think we might call it the acetoacetic ester synthesis? Because the ester we start with is commonly referred to as the acetoacetic ester. Yes, that's exactly it. Okay, where we have the aceto and we have the acetic. Whoops. Ester. In this case, this would be the ethyl acetoacetic ester. Why would we throw in the ethyl? Well, that's what's on the end. Okay. What about the malonic ester? Well, we start with malonic ester. Really creative. And if we break that down, see right here we have the mal, and over here we have the onic. At least some people are laughing. I'm completely making that up. I have no idea. That's the common name for it, right, which I like to throw at students. Name this compound for me. Water. Water. Why'd you not call it dihydrogen monoxide? Because we've been used to calling it water for so long that it's very hard to break people of that habit. Same thing's happening with these two compounds. The common name has been around, that synthesis has been around for so long, people are not breaking of the habit of referring to them by those names. So we don't refer to them based off of their IUPAC names. So when we look at those compounds, what's the chemistry that we have in them? We have acidic hydrogens. Can you be a little bit more descriptive about those acidic hydrogens? We have alpha acidic hydrogens. In the malonic ester, the bottom one, there's really only one alpha hydrogen. And in the top one, officially two, but one position that's an alpha hydrogen. In the top one, they're sure labeling it like there's only one. Isn't there another one? Isn't that also an alpha hydrogen?
Yeah, comparatively.
What do you mean comparatively?
Comparatively, the middle one is more acidic because of the resonance.
We get more resonance in the middle, so they are only labeling that one as our acidic hydrogen. Okay? We get two resonance forms as opposed to only one. Okay? Which means if we can remove that hydrogen, what do we now have? We now have a carbon nucleophile in both cases. What can that carbon nucleophile do? React with electrophiles. Yeah, super creative. Okay. So there's our acidic hydrogen. What they're referencing in this nice little slide is at the tail end. Okay. We can use just an alkyl halide, and we can do just a substitution reaction, a nice little SN2. Okay. What is special about the product produced out of that? We do have one product, yeah. What else is special about it? Now, what is special about that position?
Be more specific.
What is special about that particular position? What's that? It still has an alpha hydrogen, which means it could potentially react again. I can add another equivalent of base, and I can add another alkyl halide. Okay? So I can chain lengthen by putting in 2 alkyl groups, and I can put it in 2 different alkyl groups. That's pretty awesome. Okay? It won't happen all at once. Why would it not all happen at once? I just add the base, and then I add the alkyl halide. Why aren't 2 equivalents put on? How many hydrogens can I remove at any one time? 1, which means I only have 1 nucleophilic site. To get the second hydrogen to react, I have to add a second equivalent of base. I have to add more base and more alkyl halide. Okay? In and of itself, that isn't too big of a deal. Okay? But where this one becomes really, really special is this part. Okay? So we're taking that product that we had from the last one. We're just adding acid and a little bit of heat, and what happened?
Kicked off the...
You finish that statement and I'll accept it. You don't even have to name it.
Kicked off the other carbonyl.
The other carbonyl, that one. Anybody get a little bit more descriptive in what functional group that is? It's an ester. Interesting. How did we do that? Okay. The reason why this becomes important is depending on which we're starting with, either the malonic or the acetoacetic acid, we can add only a couple carbons. Okay. I have the potential of adding only 2 carbons to my chain. Okay. Very, very specific, and it can change the functionality at the tail end of that. Okay. So it's a pretty neat reaction to be able to do. Okay. I am well over time. Well, not well over. It's like a minute. Okay. So we'll stop with that. Okay. What you should try and do is come up with a mechanism for this. Yes, the textbook goes into detail on this mechanism. See what you can come up with on your own first. And we'll start Wednesday with that mechanism.